Hey guys, it's Professor Dave. Let's talk about electrophilic aromatic substitution.
He knows a lot about the science stuff. Professor Dave explains.
So we're familiar with the concept of pi bonds interacting with electrophiles in addition reactions. Now, when we look at aromatic systems, there are also pi bonds that are available to interact with electrophiles, but they will not do addition reactions. They will do something called electrophilic aromatic substitution. Okay, so the difference being above here, so we remember addition reactions where this pi bond is going to interact with some electrophile to yield an addition product. The difference with aromatic structures is that an aromatic system is very stable, and so there's a high premium being placed on wanting to maintain aromaticity, to try to maintain that stability. So we can see here that a benzene ring can undergo electrophilic aromatic substitution. That means this is not an addition reaction product. It is actually a substitution where some electrophile has substituted a hydrogen, or a hydrogen was swapped out for some electrophile. So it's not an addition reaction, it's actually a substitution reaction, like an SN2, just on an aromatic structure. So let's look at the generalized reaction mechanism for an electrophilic aromatic substitution reaction. So let's look at benzene because it's a simple system. So let's say we have some molecule where there's an electrophilic atom or portion of the molecule, and then A just represents the rest of it. Doesn't matter what it is. And so here's the benzene ring. We're going to see one of these pi bonds interact with this electrophile, and then the rest of the molecule will leave. And this part is very similar to an addition reaction. And so we're going to see the electrophile now coordinated to the ring, and then that left a carbocation, just as we would expect with an addition reaction. And so with a benzene ring, what we end up with is the rhenium ion intermediate, because this has three different resonance structures, right? We could move this bond here and put the cation there, and then we could move this bond here and put the cation there. Now, the composite resonance structure shows us that in actuality we have pi electron density delocalized all about the majority of the molecule. However, it does not reach the carbon that now has the new electrophile on there. That is sp3 hybridized and is not participating in resonance here. And so also the cation that can be found in any of these resonance structures is also delocalized. So we have delocalized positive charge and pi electron density about that portion of the molecule. That is the rhenium ion intermediate. Now, the difference here, this is where it becomes different from an addition reaction, because in addition reaction, some other thing, let's say some halide ion or something, would go and coordinate with the cation. That's probably not going to happen here, because let's say a bromine atom came and coordinated there. That would be a fine addition product, but then we've lost aromaticity, right? We would no longer have fully conjugated pi electrons, and so that would exist at a higher energy, so it's not a thermodynamically favorable pathway. However, if we do a substitution, so the rest of the molecule here, the A minus from before, if that goes ahead and extracts specifically the proton located on the carbon that now bears the new electrophile, must specifically be that one. If it goes and extracts that, then the electrons left behind in the carbon-hydrogen bond can form a new pi bond and thus restore aromaticity, right? We have our benzene ring back, we have the three pi bonds fully conjugated, and so this is going to be a very stable system, just as benzene was to begin with, but there's been a substitution where a hydrogen once was, there is now a new electrophile, so that's why we call it a substitution reaction. And so this is the generalized pathway for an EAS reaction. And then just to talk a little bit about thermodynamics, it can always be very useful. Let's say we have the reactants over here. We must understand that the first step is certainly the rate determining step. This is the energetically unfavorable situation where we are breaking aromaticity. Have aromaticity, we don't have it. Right, so the rhenium ion, that's the intermediate here. That's the one that is much higher energy. So the first step in any EAS reaction is certainly is endothermic, and certainly is the rate determining step. Because once we have generated the rhenium ion here, it is going to be very easy and very energetically favorable to extract that proton, restore aromaticity, bring the whole system to a much lower energy here. So here's the products. Where they are relative to the reactants is hard to say, but certainly we know that the intermediate is going to be much higher in energy than either of the two. So let's go ahead and look at some specific EAS reactions. So the first EAS reaction we want to look at is a halogenation. Here I've drawn a bromination. This could just as easily be a chlorination or something else. But we have benzene. Once again, the circle in the hexagon signifies benzene just as well as this does. So you will see that very commonly. So we want to understand that this means benzene. It's meant to resemble the composite structure of benzene, so it's actually more accurate. But so we have benzene, and then we have a bromination in the presence of a Lewis acid catalyst. So this is iron tribromide, and that is going to give us our bromo-substituted benzene product with HBr byproduct. So let's try to understand how that might work. So the reason we need a catalyst is that it's too energetically unfavorable for benzene to interact with bromine. In order to break aromaticity, which is highly energetically unfavorable, that's not going to work simply with bromine. We need the presence of some kind of catalytic complex. Now, if we recall, a catalyst is something that lowers the activation energy of the reaction while not being consumed in the process stoichiometrically. So here we have a molecule of bromine. This is going to interact with the iron tribromide. So this is acting as a Lewis acid because the iron atom is accepting electron density. It's acting as an electron acceptor. That's what makes it a Lewis acid. And so so we have the bromine lone pair here is going to go ahead and coordinate to this iron atom. So we're going to generate a new covalent bond between the bromine and the iron. So this is the catalytic complex. Now the key feature here is that this bromine has a formal positive charge, right? Because it's contributing 6 electrons to this Lewis dot structure, 1 per covalent bond, and then 2 lone pairs, right? A halogen atom is typically participating in 1 covalent bond. So this is an uncomfortable situation for a bromine atom. It is going to have a formal positive charge, and then it also donated an electron to the iron atom. So now the iron atom has a formal negative charge. So this is the key complex here in order to promote this EAS reaction. So benzene, while it could not interact with a molecule of bromine by itself, it does have an easier time working with this, because if this pi bond interacts with this bromine atom, then these electrons are able to go and neutralize this bromine atom. So anytime you neutralize a formal charge, that is an energetically favorable situation. And so that's what makes this step have a lower activation barrier than benzene simply interacting with a bromine molecule. So that's why this is able to work. So now, just like any other EAS reaction, we've got this pi bond interacting with this bromine atom. So that's on there, and we've left a cation. So this is our rhenium ion intermediate. I didn't draw the other resonance structures, but we remember what those are. And then what happens is that, so here's the rhenium ion intermediate. Now we've got the remainder of this complex, right? This bromine has been neutralized by those electrons, as we saw before, but this iron atom still bears a formal negative charge. So what that means is that it's very happy to lose a bond, because in losing a covalent bond, it itself will neutralize. So that means that bromine, along with these electrons in this covalent bond, in other words, Br minus, or a bromide, is going to dissociate from this complex, go ahead and extract the proton. The electrons in this carbon-hydrogen bond are going to go to form that pi bond, restore our aromaticity. And what else has happened is that Br minus and H plus gives us an HBr, and then the rest of this, the iron is neutralized by losing that electron, and we regenerate our Lewis acid catalyst. So This is how halogenation would work. If it were chlorination, this would be Cl2 and FeCl3, and the mechanism would be absolutely identical, just replace every bromine with a chlorine. And so that's how this is going to work. If we look closely, we can also understand how this looks just like the generalized mechanism that we looked at before, right? We had benzene, and then we had EA, right? So this was the electrophile that was E, and then the rest of this is simply A. And then later, the rest of this that was simply A, but A minus, went and grabbed the proton, and then we restored aromaticity. So we do have byproducts, but it does look just like the generalized mechanism we looked at before. And then the only other thing we need to understand is what this Lewis acid catalyst is, what it's doing, and then why it's necessary to be able to promote this reaction. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me with questions, ProfessorDaveExplains@gmail.com.